Absolute value and distance. If x and y are real or complex numbers, such that y equals x squared, then we call x a square root of y. So y is the square of x, but x is a square root of y. If x is a positive real number, then we say that x is the positive square root of y, and we write x using the square root symbol, x equals root y. For positive real numbers, we will use the square root symbol only for the positive square root of the number. For complex numbers, we'll use the square root symbol for the principal square root of the number. The concept of principal square root is not going to be discussed in this lesson. That'll be discussed in a later lesson. Let's look at some examples. Since 2 squared is equal to 4, 2 is a real number and 2 is greater than 0, we see that 2 is the positive square root of 4, and we can use the square root symbol to write 2 equals root 4. The square of negative 2 is also 4, but negative 2 is less than 0. And so we do not write negative 2 equals square root 4. However, negative 2 is still a square root of 4, and we could see from the above equation that negative 2 is the negative of the square root of 4. Since I squared is equal to negative 1, we see that I is a square root of negative 1. Since the square of negative I, that's negative I times itself, negative I times negative I, that could be written as negative 1 times I squared. Now, negative 1 times negative 1 is 1, and I squared is negative 1, so we get 1 times negative 1, which is negative 1. So we see that negative I is also a square root of negative 1. The square of 1 plus I, using the definition of a power, is 1 plus I times 1 plus I. And then using the definition of multiplication of complex numbers, we get 1 minus 1 plus 1 plus 1 times I, which is 0 plus 2I, and that could be abbreviated as 2I. So 1 plus I is a square root of 2I. The absolute value, also known as the modulus of the complex numbers z equals a plus bi, is the non-negative real number, absolute z, is equal to the square root of a squared plus b squared, or equivalently, the square root of the real part of z plus the square of the imaginary part of z. If z equals a plus 0i, or a, is a real number, then we could see that the absolute value or modulus of a is just the square root of a squared. This is equal to a if a is greater than or equal to 0, and negative a if a is less than 0. For example, the absolute value of 4 is the square root of 4 squared, which is square root 16, or 4. And the square root of negative 4 is the square root of the square of negative 4, which again is the square root of 16, or 4. If we write that as the negative of negative 4, then we see that the absolute value of negative 4 is the negative of negative 4. Geometrically, the absolute value of a complex number z is the distance between the point z and the origin. Let's look at an example. Which of the following complex numbers is closest to the origin? 1 plus 2i, negative 3 plus I, or negative 2 plus 3i? Well, the absolute value of 1 plus 2i is the square root of 1 squared plus 2 squared, which is root 1 plus 4, or root 5. The absolute value of negative 3 plus I is the square root of the square of negative 3 plus 1 squared, which is the square root of 9 plus 1, or root 10. And the absolute value of negative 2 plus 3i is the square root of the square of negative 2 plus 3 squared, which is the square root of 4 plus 9, or root 13. Okay, we see that root 5 is the smallest number that came out, which means that 1 plus 2i is closest to the origin. The definition of the absolute value of a complex number is motivated by the Pythagorean theorem. Let's look at an example. Let's look in this figure at the complex number -3 plus I. Observe that to get from the origin to the point -3, 1, we move to the left 3 units and then up 1 unit. This gives us a right triangle with legs of lengths 3 and 1. By the Pythagorean theorem, the hypotenuse has length square root of 3 squared plus 1 squared, which is root 9 plus 1, or root 10. Right? So the absolute value of -3 plus I is the square root of 10. The distance between the complex numbers z equals a plus bi and w equals c plus di is, distance between z and w is the absolute value of the difference z minus w, which can be written as the square root of the square of c minus a plus the square of d minus b. Let's look at an example. So this figure shows geometrically the computation 1 plus 2i minus 2 minus I equals -1 plus 3i. Right? So you could see the vectors 1 plus 2i and 2 minus I there in blue, solid blue, and then we negated 2 minus I and drew -2 plus I in dotted blue. Using 1 plus 2i and -2 plus I, we finished the parallelogram, and then we were able to draw the vector -1 plus 3i, right? That's geometrically equivalent to adding the vectors 1 plus 2i and -2 plus I, and that's equivalent to the subtraction that we wanted to show. Geometrically, we can translate the vector z minus w so that the directed line segment begins at the terminal point of w and ends at the terminal point of z. Okay, so here we see we've moved the vector over so that it begins at 2 minus I, the vector we're subtracting, and ends at the terminal point of 1 plus 2i, the vector we're subtracting from. Notice that the expression for the distance between the two complex numbers follows from a simple application of the Pythagorean theorem. So here I superimposed a right triangle over this picture. We could see that the legs have lengths 1 and 3, and the hypotenuse is going to have length absolute -1 plus 3i. Right? So we see that the distance between 1 plus 2i and 2 minus I is the square root of 1 squared plus 3 squared, which is root 10. Theorem 7.3, the triangle inequality. For all complex numbers z and w, the absolute value of z plus w is less than or equal to the absolute value of z plus the absolute value of w. Geometrically, the triangle inequality says that the length of the third side of a triangle is less than or equal to the sum of the lengths of the other two sides of the triangle. As an exercise, you should prove the triangle inequality. It's not too difficult. Let's look at an example. Okay, here we have a picture of some vectors. We see 1 plus 2i plus -3 plus I, and then using the geometry with the parallelogram, we get the vector -2 plus 3i. So by the triangle inequality, the absolute value of -2 plus 3i is less than or equal to the absolute value of 1 plus 2i plus the absolute value of -3 plus I. Okay. evaluating those, we see that the square root of 13 is less than or equal to the square root of 5 plus the square root of 10.